Today I'm going to give a brief update about the status of the simulations that we are having now in EERIE. So I would like to thank also others, Malcolm, Jürgen, Pablo, and Matthias for preparing the materials for the other modeling centers and providing the material for today's presentation. So first, a little bit brief about what simulations that we are expecting. So we are now in the phase one, almost at the end of the phase one, you can say. And we are expecting CMIP6-like simulation from Met-Office in EERIE. They are supposed to run HADGEM3 GC5 model in 3 different resolutions of low, medium, and high resolution. CMIP6-like, so it starts from 1850 and they aim to go until 2100. And then we have another category of simulations which goes below 10 kilometer in atmospheric resolution and also ocean resolution in almost around 5 kilometers. And in that simulations we perform in high-res MIP-like, so it starts from 1950 and we aim to go at least until 2050. So, and the participating models are ICON from MPIM and IFS NEMO from BSC. BSC also performs a lower resolution, medium resolution version simulation with the same model. So they have 10 kilometer and also 25 kilometer. And right now, AVI performs the IFS FISM simulation. And apart from that, we also have AMIP simulations from ECMWF, which performs AMIP-like simulations and also filters the AD features and tries to give us an understanding from AMIP-like simulation in 2 resolutions, one with 9 kilometer and one with 28 kilometer. So first we start with Met-Office. So the present status is Met-Office has completed their low resolution, medium resolution, and high resolution simulations of CMIP6 pre-industrial control, historical, and SSP 24.5. So in the right, you can see the GM global mean surface air temperature time series of different simulations to give you a visual feel of what kind of simulations are already have performed. So they are also cross 2050 in their high resolution version. So they're at moment at 2073 and the progress is happening gradually to reach to 100. So pre-industrial control is of 200 years and also historical and future scenarios are supposed to be as we expected. So regarding the available data part, so they avail the regridded data of atmosphere, ocean, and sea ice, which is available in Jasmine or also could be accessed through DKRZ machine, Levante, and also it has monthly and daily data, and the summarized data is also available in Jasmine and published in the KIDA archive. So there are some, right now they cannot provide any estimate of high resolution when it finishes, but it's on the way. Next is ICON from Max Planck Institute. So they have completed their historical simulation of the phase one, scenario simulation until 2050, and also control simulation. So their phase one simulations are basically what was expected are all complete at the moment. And you can see overview of their simulation, the same global mean annual surface temperature time series, and their data are all available in Levante. Native grid and regridded data, daily, monthly, 6 hourly, and also the summarized data is ongoing. Summarization of the data is ongoing right now. So basically from ICON perspective, they're kind of complete with their phase one, everything. And then comes to IFS NEMO, which is from BSC. They also performed simulations in 2 resolutions. So they have a historical simulation complete, phase 1 in 2 resolution. And also scenario simulation is ongoing at 10 kilometer resolution, as we understand from this global mean surface air temperature figure at the right. So they have a control simulation also from 25 kilometer and 10 kilometer ongoing right now. So they are almost getting complete. The 10 kilometer and also 25 kilometer also is catching up. And the data are currently available in Levante. So we have the data in historical and control runs, 10 kilometer, daily, monthly, and 6 hourly. So regraded data are mostly all available right now, and all the most other experiments and data will be transferred by October. And if you have any queries, you can ask, you can contact Pablo Ortega to get more clarity about which data when we can get. And here you can see a time series of what's happening in those runs. We don't go to so much science details right now, so we move to the next model, which is IFS FISOM, which is run by AVI. So we are completed our historical simulations, scenario simulations until 2050. We wanted to go a little bit further, so we also did 10 years more at the moment of the scenario simulations, but based on what resources we have, we decided to stop at the moment and see we have enough resources to do other simulations that are coming. And the control simulations is right now almost 75 years kind of complete, and then we need 25 more years, so we would be complete with the control to go until 2050 this month, so by the end of this month. So regarding the data, again, full historical scenario data are available in Levante. Control is available until 2014. Here you can see the GMS3 time series, global mean surface area time series in those runs. So these all data until the control is 2014 are available. Regraded data, atmosphere, ocean, and the ocean 2D is only regraded at the moment available, and the native grade we will add later, as right now with the regraded is available. And now at the end, we go to IFS AMIP simulation. So the IFS AMIP simulation has performed a reference simulation of AMIP type simulation in 2 resolutions. As you can see in the table, they have 1 member for 9 kilometers. And so these simulations are performed and done quite some months ago, but I wanted to give an up again to highlight that these simulations are also available, and we can do many analysis with this data. And then they have 2 other kind of smooth simulation where this filter the eddies in the SST, the signature of the eddies, and perform simulations. In 28 kilometers, they have all simulations have 10 ensemble members, and in 9 kilometers, they have 1 member. And these outputs are also available in native and quarter degree grid, 6 hourly, daily, monthly means in Levante. Many data are available in the Mars. You can get all the data complete, and some subset, the monthly means in quarter degree, you can get also in Levante. And also 1 year of complete native data. And here you can see the time series from this run that you can see, of course, AMIP runs, and you have good agreement and complete time series. And at the end, just to summarize for the moment, we have now EERIE phase 1 kind of almost the overview is simulations are finishing almost there. Many institutes already completed their simulations, and data are also getting updated by the end of in this month. So all the data, basically what we can see right now as a summary of all this that I have told you right now, that the regraded data of all the models kind of available in Levante. That's my understanding, what I understood from this information. And right now we are also planning for the phase 2 simulations, and they will also resume soon. So on that kind of the summary, and now you can ask if you have any questions regarding this information.
Thank you very much, Rohit. Are there a few questions for Rohit, or? I had a question, Rohit. I think you are planning a paper describing your simulations. Is
Yes.
this is the preprint going to be available soon?
Yeah, hopefully preprint. Yeah, we are almost at the end of the drafting the paper from our side, so hopefully we will have a preprint by maybe in October. I can see. Yeah.
Well, thank you very much. It will be very interesting to read it. Katja?
Yeah, thanks a lot, Rohit, for the summary. I was wondering, at least for the summarized data, there are some differences. Which variables are provided by which model? Will there be some kind of unified list? For example, I know that Jan was missing the wind stress on the ocean grid and was wondering if you should switch to atmospheric grid or if all models will have it on the ocean grid at some point, things like that.
Oh yeah, that's a good question. So yeah, right now the summarization of our model at least, and ICON is performed by DKRZ, so they would have more details of which variables they are providing to making the summarization. And so, but it's a good feedback. So we will try to, maybe it's good to have a list of which variables are summarized and listed in one place so that we can make it available to clear information that these variables you can get. Regarding these wind stress variables, for us, I think that in IFS models, this variable was available in the atmosphere side. So we kept not getting it from the ocean side. At least it was from us. That was the case. I'm not sure about IFS Nemo, but yeah, from us it will be from the atmosphere. So yeah, I will also keep that in mind to make it clear. Maybe we can, when we summarize the atmosphere data, then we will have it also there.
Yeah, I think the atmosphere was there. Jan was looking for ocean and was wondering why it's there in ICON and not in IFS, if I remember correctly. Maybe it was the other way around. I don't really know.
IFS, we have it in the atmosphere side, so we put it off kind of.
Hi, just a question, maybe for Pablo, because you were talking about the 25 kilometer at BSC, which is great, and I just wasn't aware. There seem to be quite a few runs at BSC recently, which is really great to see, like these 25 kilometer runs. And first, I would be curious if you could just do one member, and then it would be if you could say a few words how they relate to like the 9 kilometer ensemble done in the Destiny context, and you also have various 25 kilometer runs ensembles there. Are they all the same, or are they perhaps somewhat different? I would be curious. Thanks.
So yeah, the control and historical at 25 kilometers, we only have one member. We would like to run some ensemble too, but we've been giving priority to the 10 kilometer ones because those are also much slower to run. We can always produce a couple or more ensemble members at 25 kilometers in a short amount of time. Then you were asking about the comparison between the Destiny ensemble and the one in EERIE. Am I right?
Yeah, I mean, I just heard last week, I think, that you have this 50-member, I believe, ensemble. Is this comparable?
Okay, yeah, that was something that Kai produced, but to understand bit-to-bit reproducibility. Well, not bit-to-bit reproducibility, but basically reproducibility in the model, not to what extent we can trust, we can judge that the model is going to reproduce always the same in-state climate. And he didn't pick a model version with good climate. I think it was based on phase 1 in Destination Earth. So it's a large ensemble, but it's not very good in terms of the mean climate. So that's the one with a lot of members.
Okay.
Then at 10 kilometers, we have a historical and future projection ensemble of 3 members, but then it's starting in 1990 and it's finishing in 2050. So it would overlap with the one in EERIE. But it has this problem of the initialization, like the spin-up is really, really short and it suffers still from moderate drift.
Yeah, I think that could be very interesting to sort of have these different data sets, especially if the model version is very similar, which I think it should be. That like it's always hard to know for sure. then this could be really interesting data sets, like what difference the much longer spin up of the EERIE simulations does. And if you have ensembles, that will really help that to get to the variability.
Yeah, so that's something we plan to do. We will prepare. We will be preparing a paper documenting IFS NEMO in EERIE, in Destination Earth, and all the experiments that we have. And one of the things we want to address in that paper is how these protocols impact the conclusions. So we want to take advantage that we have these ensembles that overlap for most of the extension and see what we can learn from them. In particular, for Destination Earth, that is the one that you can criticize in terms of spin-up period.
Great, thank you.
Well, thank you very much. And I think it is time for us then to switch to the presentation of William. So William is a researcher at CNRS in Brest, working in the same lab as myself. And so you have the floor, William, if you can share your screen.
So thank you, Anne-Marie, for inviting me today for giving this talk. So I will talk about the trend in regional sea level and how we participate in ERIE and take care and consider the simulation all the center are doing. So as Anne-Marie said, we are interested in sea level change, and for that we have now for more than 30 years a very powerful tool which is called the satellite altimetry, and from those data we can compute such a map which shows the regional sea level trend over 1993 and 2023. So we know that sea level is rising at global scale, but its rise is non-uniform and present large regional variability. And one of our interests here in the lab is to understand why we have such a large regional variability, and can we interpret those change. So we are interested in that because it's highly relevant for coastal communities, as we know that 10% of the world population lives in a coastal area. So the outline of my talk will be split in two parts. I will first present you a recent study we have made on understanding the regional sea level trend based on only observation. And the second part will be more related to what we are doing in ERIE to try to estimate the externally forced and internal climate variability on those regional sea level trends. So I will start with the observation. So starting from the hydrostatic equation, it's kind of easy to obtain this equation, meaning that the sea level change on the left can be partitioned into two terms: the steric sea level change, which is related to the density change in temperature and salinity, and the mass change, which is related to the freshwater income from the ice sheets and mountain glacier and groundwater storage. Since 2005, we are in the golden age for the sea level studies, because each parameters can be measured by observing system. We have satellite altimetry for sea level. For the steric part density change, we have now quite near global coverage of the Argo profile that records temperature and salinity down to 2,000 meter depth. And for the mass component, we have the GRACE satellite, gravity recovery and climate experiment, that records change in geoids over the ocean. So thanks to those observing system, we can try to see if each parameter can be properly assessed. So this is what we have done over 2014-2023, the last decade basically. So we have compared the regional sea level trend inferred by satellite altimetry on the upper left. So we see that we have larger trend value for the western tropical Pacific Ocean, and even some negative trend in the eastern equatorial Pacific Ocean. And I've plotted the steric sea level trend on the upper right and the manometric trend, the bottom map. So we can clearly see that on decadal time scale, the density sea level trend explains a large part of the spatial pattern observed by the satellite altimetry. For the mass term, we call that the manometric sea level trend. we can see that the values are an order of magnitude smaller than the steric term. So because the Argo float record temperature and salinity, we can partition the steric map into the temperature related sea level and the salinity related into sea level. This is what I've done here. On the left side, I showed the thermosteric sea level trend, that is express the temperature change in terms of sea level. On the right is the halosteric sea level trend. So at a first glance, we can see that the temperature change explains the large regional pattern observed by the Argo float for steric sea level, but even for satellite altimetry. On the right, we can see that salinity can enhance or reduce the regional pattern observed by the Argo float. And for this study, we get interested in this particular area in the western equatorial tropical ocean because we see that there is a drop in halosteric sea level trend. This means that there is an increase in salinity. This area is of great interest because there are many islands and low-lying coastal region, and we know that this region is one of the most vulnerable to the future sea level rise. So we decided with my colleague to investigate this region located with a mask here in a western tropical Pacific Ocean. So what we have done first, we took a look on the salinity changes in this region, the black line that delimits the mask, and we have plotted the mean salinity, the regionally average salinity as a function of depth and time. See what I show here on the left. So we see that we have an increase of salinity located near 2,300 meter depth, especially with large values starting 2018. So computed the trend for this diagram, and we found that we have quite of interesting salinity trend located 2,000 meter depth, reaching 0.015 PSU per year. So one of the results here is we saw the maximum of salinity in the for the upper part of the ocean, but even at 200 meter depth. So we decided to investigate what kind of potential mechanism lied into this upper ocean salinity, and for that we decided to apply the heave and spice decomposition. So Bindorf McDougall in 1994 put this framework quite nicely. And we know that the salinity change in isobaric surface can be decomposed in salinity change on isopycnal surface, which is the spice component, plus a term which is the vertical movement of the isopycnal. We call this one the heave. So we'll interpret the spice component as the salinity change propagation along the isopycnal surface, whereas the heave component will be interpreted like the vertical movement of the isopycnal. So we have partitioned this regionally average salinity for this region. On the upper right here, this is the spice contribution, and below this is a heave contribution. So we found that both heave and spice are contributing to this observed salinity change, but we found that the pattern for the heave are very similar to what we observed for the total changes, especially for the end of the time series. Regarding the salinity trend as a function of depth, so we found that at the surface, we found that there is a slight salinization. This is the blue curve, and this one is due to the heave, to the spice component, largely offset by the heave component. And for the 200 meter depths, we found that both heave and spice contribute quite equally, 50% each, to the salinity increase. So we try to go try to explain how those changes can be done. So we try to see if there is any local or remote atmospheric that could contribute to both changes. So we start to have a look on the precipitation minus evaporation trends from ERA 5 atmospheric reanalysis. And we found that over 2014-2023, there is a decrease in this precipitation minus evaporation located north of the region of interest. So this decrease we decompose into precipitation and evaporation, and we found that almost all the negative signal can be attributed to the precipitation trend. So basically, we found that there is a precipitation deficit over the period of interest and just north of the region we delimited with the mask. So we try to understand if there is any local or remote contribution to this precipitation deficit that could be linked to this increase in upper ocean salinity. So for that, we decided to have a look on the Ekman pumping and based from ERA 5 reanalysis, and we have estimated the time mean, the map of the temporal mean of Ekman pumping over 2014-2023, and we found that over the region of interest, there is a time mean upwelling for this region. So basically, the time mean of the Ekman pumping cannot explain any propagation of salinity anomaly from the surface to 2,000 meter depth. And we also compute the trend, and we see this upwelling tend to diminish in terms of as a function of time. So we do not find any clear local atmospheric forcing that could advect the salinity anomaly from the surface and link to the deficit of precipitation to the 2,000 meter depth of the ocean. So we try to investigate if there is any possible remote wind forcing. So for that, we have plotted the allosteric sea level anomaly of Mueller diagram from 5 degrees south to 15 degrees south, or 160 degrees east to 95 degrees west. And what we found, that there is a wave propagating signal generated near 120 degrees west over there, with one positive anomaly propagating westward and one negative anomaly propagating westward. And those two signal can explain the decrease in allosteric sea level we found in terms of trend, which is denoted with a blue box here. And we try to assess which kind of wave could be responsible for this signal. And based on the Rossby wave theory, and thanks to this diagram, we found that there is a wave speed of about 40.4 centimeters per second, which is in line with the Rossby wave theory. So all these results have been summarized in a recent paper that is in press in Geophysical Research Letter. So I'll now jump into the second part of the talk I'm presenting to you today, which is related to external force and internal climate variability on regional sea level trend. So again, I would like to show this map of regional sea level trend. One of the big questions of the scientific community interested in sea level is to understand what are the cause of the large regional variability we observe with satellite altimetry, and if those regional patterns are a direct response of external forcing. So for you, I'm sure the definitions are quite clear, but I would like to remind a little bit. So by external forcing response, we are talking about the variation caused by factors outside the climate system that would be natural and or anthropic. And for internal climate variabilities, is unforced climate change or more variabilities that do not involve changing the Earth's net relative balance. So what they have done so far to assess this, try to address this question, is to use climate model ensemble simulation from the CEMIP archive, and basically scientists used to consider an ensemble of opportunity mixing any of the climate model output available for estimating both responses. And thanks to, based on the ensemble mean, people used to interpret the ensemble mean being the externally forced response, and for the ensemble spread will be linked to the internal climate variability. So this is which have been done by Palanisamy in 2015. This is the ensemble mean trend based on CEMIP FAP 5 archive for the regional sea level, and they found that there are quite positive sea level trend greater than 1 or 1.5 meters per year in the North Pacific Ocean off of Japan coast and in South Pacific Ocean off of New Zealand coast. We have to see that those trends are quite small, less than 2 millimeters per year, but there is an important limitation of this approach because they are mixing different climate models that could present different error or bias. So because now we have access to ensemble for each for several climate model, we try to reassess with a colleague at LOPS this approach to partitioning both responses, externally forced and internal climate variability. This is what we have done here. The map on the left, this is the ensemble mean for the regional sea level trend computed over 1993-2014, based on 24 different climate models with only one simulation per climate model. On the right, this is the ensemble spread of the regional sea level trend over the same time period. So what we see is that the results are quite consistent with Palanisamy. We find very small positive trend in the Pacific Ocean. However, we find larger trend in the North Atlantic Ocean and in the Arctic, up to 4 millimeters per year. In terms of internal climate imprint, we found that the energetic region, such as Kuroshio, the Gulf Stream and its extension, or even the ACC, present larger internal variability. However, with this approach, we mixed the external force response and the internal climate variability with the intermodal variability because we are mixing different models. That's why we try to assess the same responses based on different ensembles, based on different climate models. So we consider 24 members for each climate model. And here I propose to show you the externally forced response for the sea level trend over the same period. And we see that from one ensemble to another, we find that first, that all climate models tend to simulate smaller trends than that are observed by satellite altimetry. This is a very important point. And second, we found that there is some kind of discrepancy in terms of the climate model to simulate spatial pattern in sea level trends, especially for the externally forced response. And more, we found that two climate models, North CPM1 and CNRS, present smaller trend amplitudes compared to the others. Thanks to those 8 maps, we can compute the standard deviation and find where the climate model tend to agree or disagree. And this is this map. This is intermodal variability from the externally forced response. And we find that we have divergence from climate model for the ensemble mean, especially in the North Atlantic Ocean, where we find that the ground can reach 4 millimeters per year. In the Arctic, it's around 2 or 3 millimeters per year. But even in the Pacific Ocean, we can find differences based on the intermodal variability for the externally forced response up to 2 millimeters per year. So this question, the result made by different research groups based on the ensemble of opportunity, are they really estimated the external force response in sea level trend, or is it an imprint of the intermodal variability? And second, so for investigating the climate signal in sea level based on satellite altimetry, we need to reach an accuracy on 1 millimeter per year. And we see that for the observation. And we see that depending on the approach we are doing for the external force response, we can see that in some region we can exceed 1 meter per year to attribute any externally forced signal. And I would like to finish this talk to have a look on the internal climate variability. So this is the internal climate variability for the regional sea level trend based on the 8 large ensemble we have considered with 24 members. And we see that the different climate model simulate large spread for the energetic region like Kuroshio, Gulf Stream, and even ACC. But still, we found that the climate model present large differences in regional climate variability. And thanks to that, we can find this map. This is the mean of the 8 previous map. And this one is the real internal climate variability, which is common to all the 8 ensemble. And we find that the large value larger than 3 or 4 milliliters per year in the energetic region. And so we can compare those two estimates. On the left, the internal climate variability imprint to regional sea level trend, and on the right, the internal climate variability and the intermodal variability imprint on the right. And we see that we can find the differences, especially in the Pacific Ocean, from the differences from 2 or 3 milliliters per year in the South Atlantic Ocean as well. And even in the North Pacific. So this question, the conclusion raised by several studies in interpreting the internal climate variability on sea level trend. So with this approach, we can easily partition what is done to internal climate variability and what is due to intermodal variability. And I think I will stop here. Thank you.
Thank you very much, William. So are there questions for William? I can start with one question. William, you didn't say what you could be doing with the high-resolution EERIE models.
Yes, that's right. Yes. What we want to do with the high resolution is to investigate the internal climate variability. So we see that from one climate model to another, we have large differences in spatial pattern for the internal climate variability. So one question we would like to address with the EERIE simulation is the evolution and the changes in internal climate variability with the same numerical model, but with different resolution for spatial resolution. So we started some investigation with AGEM simulation based on the pre-industrial control simulation, and we compare the spread for the internal climate variability for AGEM at 1 degree, quarter degree, and 1/12 degree. And we found that there's some differences, especially in Western currents, because they are better resolved. And we would like to investigate what we gain when we increase spatial resolution, basically. But I didn't show any plot today on that.
Thank you.
Any other question?
Well, maybe I have another one then.
Yes.
I mean, the studies that you did of this specific region in the Pacific, that was over a very short period of time, so 10 years, and those Rossby waves, so this was mainly internal variability and nothing to do with climate change, right?
Definitely, yeah, definitely. Because in terms of climate change, this region tend to getting fresher and fresher. And what we show basically that when we assess the decadal sea level trend, we can still have the imprint of climate mode of variability, and this is linked with ENSO, basically because we have 3 La Nina in this region that leaves imprint in sea level trend. These studies basically highlight complementarity between different observing systems with space, with remote sensing data and in-situ data. And we highlight the need that we need in-situ data to interpret the satellite altimetry data.
I don't see any other question. Perhaps I have another one, which is, I mean, you pointed out that now we have 30 years of satellite altimetry. So do you think that when we investigate the sea level over the historical period with the EERIE models, we could just take the historical run and then the first 10 years of the scenario to be in a framework where we can assess the models with respect to what was observed, but over the full altimetry period rather than just stopping in 2014.
Yes, you're right. This is one possibility. Yes, but we can also consider sea-level reconstruction that merge satellite altimetry and tide gauge data, because we can get back until 90, basically. So we can cover the 20th century, but this is a reconstruction. Do you know reconstruction, Anne-Marie? No?
No,
No?
but
People? Yes.
1990.
No, before.
Before 1990. Oh, okay.
Yes,
No.
yes. Because you can transpose the satellite altimetry data variability onto tide gauges and try to reconstruct what happened before the satellite altimetry era. So this is one other possibility. We can discuss that offline if you want one day.
Okay, sure. Pablo?
I just wanted to comment that for me, it's better to focus on the satellite era because you can benefit from very high resolution data, no, in altimetry that you wouldn't get with this reconstruction. And it's when you can actually make the most of the simulations in EERIE, no? Trying to see to what extent they improve the agreement with the observed trends, no? With 30 years, you can assume that most of the variability is forced. I don't think it's true, no, but I mean, it's
no, it's not true.
It's not exclusively forced, no, but a lot of the decadal variability might cancel out, no. And it would be interesting to see how the EERIE models perform, and for that, I think it's pretty good to do what Anne-Marie was suggesting of combining the historical and the future scenarios. Especially once we have the ensembles in which you will have different possibilities of force strength. You could see whether for this particular high resolution simulations, you have a better the ensemble is within the observations are within the spread of the ensemble, in some way.
Yeah, definitely. But which SSP do you consider for that? The 8.5 or the 6.5?
Is
to go beyond 2014.
4.5, but I don't
8.5.
think it's really relevant because it's only for the initial period, no? So it's from 2014 to 2025. 2025, you might be able to include it, no? It's 11 years, and the scenario won't make a big difference in terms of the trends. And also, I would expect some dynamical aspects, to be radically different in nature, in the EERIE simulations, and that's where you can hope to get a better agreement with observations.
Yeah, it's a good point. Yes. Yeah.
Any other comment, question about regional sea level? No. So I think we can first announce next month's seminar. It will be made by Christian Stroman about the effect of eddies on the atmospheric circulation, and it will be based on work in WAR Package 7 and deliverable 7.1. So you are all welcome to attend the next month's Storm and EERIE seminar.